Oh man, it's a trip.
So what do you think, Oliver? You think we ought to get going?
Yeah, absolutely. Hi everyone. I'm Oliver Weiss, part of the Birmingham Elixir team, or founders. Me, Josh Adams, one of our founders, and Kevin Brown, the other founder. We're here just to kind of relax after a long month's work and be able to learn from people like Bruce. Bruce, thank you very much for joining us. I believe tonight's talk is on machine learning, and reach out to one of the founders if you'd like to speak or sponsor or have any other involvement. Thanks, everyone. And without further ado, turn it over to Bruce.
Yeah, it's been really fun to do this group with Erlang Solutions, and so we're from Groxio. So Maggie and I, and Maggie, blink your mute if you want to kind of show. Yes, we're really representing here,
Hey, I
and
had a light leak, so I was turning off my video.
yeah, you're more dazzling than usual. So yeah, so one of the things we do, a couple of things that you might be interested in. The first thing is that we have some professional courses for mostly OTP and live view. We're considering putting some courses together for Axon and Elixir NX once it settles down some. So that's the first thing. The courses come every month. Check our schedule, grox.io. You can check our schedule for professional trainings. So the second thing that we do is for people that prefer a self-guided approach, we have some free content, some free videos and things like that. We have one coming out for that will basically be a version of this talk, but with some music and things and probably at a more rapid pace. Um, but we also have a subscription. So what will we cover? Well, we publish about 6 to 12 months in advance on what's going to happen. And our next year now looks like, so we're just finishing up going through Julian Flux, and then we're going to move into Elixir Ecto, and then we'll move into Elixir NX, and then we'll move into Flux, which is the Julia machine learning framework, but we're going to be doing vision with Metalhead. And I find that the combination of Elixir and Julia go really well together because Elixir is a really elegant language for expressing math. And Elixir is better around the edges for the things related to data and processing. So if you want to check those things out, feel free to. grox.io. If you do choose to subscribe, reach out to Maggie and we'll see that you get a deal. What happens is that an annual subscription is an all access pass, and you get to keep basically the year's worth of stuff that happened when you subscribed, that was released when you subscribed. But we'll make sure that you can keep everything going back about another 12 months or back to when the original Elixir stuff was published. So you can get keep forever the Ecto stuff, the live view stuff, and the OTP stuff, and also nerves. So we're going to talk a little bit about Axon, and that is an Elixir project that's in the umbrella of NX. So who can tell me why Elixir was not seen as a traditionally great language for doing numerical style computing?
I mean, I guess what I've heard is that it's a high level language that was not particularly fast and also functional. So a lot of what people have done is, use mutable paradigms to get speed, which was always very important.
Yeah, so there's a couple of things in there. One, it's high level, which is definitely true. Not fast, and that kind of depends on context. If you look at Elixir in like straight line speed, how many numbers can it crunch? It almost always loses those benchmarks and kind of makes up for it with clean abstractions and really excellent concurrency and really excellent consistency. And so the other thing that you said that I definitely agree with is there's this idea that when you're immutable, you do things with your data structures that aren't always conducive to it's funny. I'm talking with my hands, and my Fitbit just went crazy. I got my 10,000 steps in, so I'm sitting still and getting fit. So I might have to junk this thing, right? But so the idea is that there are some things that that Elixir does that aren't super conducive to um, processing things like numerical computing. So let me just give you a single example. So let me keep asking questions. So if I say hi and I say hi, is this true or false?
False.
Oh,
Why? Why?
Because one's a list and the other's a binary.
Right. So the idea is that bind art. The idea is that this is probably a more efficient representation if all you want to do is cram numbers together, leave them alone, and then send them around, right? It's not. Excuse me. So it's not very efficient algorithmically. And the reason is that basically this. So if I did something like this, this is a binary format, right? If I said 97 question mark 98 and 99, what did I do? Oh, how about A? C, right? And so that's a string. And the other way around, if I did a 97, 98, 99, this is a list, right? And this is actually 4 lists that are chained together. These are linked lists, right? This is a C, which is what, a 99. It's like a 99 concatenated with an empty list, right? And it is a B, so I would concatenate a 98 to that, right? And then so on and so forth, right? So it's efficient in one perspective that once I have a list established, if all I ever mess with is the very first byte, everything is going to be super efficient with Elixir's list. But often with numerical computing, that's not really what you want to do, right? So there's a couple of other things as well, like Elixir's numerical support is based on Erlang's numerical support, and by default, you get something that auto upgrades from in terms of precision, and so it's hard to build efficient in terms of representation lists of things. And numerical computing is often all about building these huge lists, right? So what we're going to do, I have installed a couple of dependencies in this project called XOR, which is, I was just kind of playing with an XOR gate. And I want to show you that I've already added 3 dependencies. I want to kind of show you what those are. So the dependencies are NX, and this is numerical Elixir. This is 2 things. It's an umbrella project that has all of the numerical projects for Elixir, and it also has the things like tensors, which is multi-dimensional arrays, and it also has efficient numerical computing and some things like that. Right? There's EXLA, and this library is essentially compiler support, so we can do things like plug in Elixir's numerical definition, so that you could have like defn, and that will have functions that are defined in there will have more efficient behaviors in terms of numerical computing. And it also has Axon, and this is the one that we're going to use tonight, right? So this framework is all about machine learning. So I'm going to jump in an IEX session. And I would be doing this from Lifebook, but I'm not fluent enough. When things break, they break bad for me, and I can't get it back together. So I'm going to be doing this from IEX. So I'm going to just open the session, and this S-Mix means start this as a mix project, which means that we're starting the project in the context of these dependencies and this application, right? So Mix is just the tool that builds that application and provides development time and test time and production time tasks that that support that process. Okay, so we're going to require Axon, and so I want to talk a little bit about machine learning. So find your chat in your Zoom window. We have a lot of time, right? So I'm not going to take the full hours, but full 2 hours, but I can take maybe an hour 15, hour and a half. Is that okay, Oliver? Okay. So, and if you need to step off early, it's fine. There's going to be another couple of versions. There's going to be a video version of this that's going to be a little bit faster. Then there's also, if you sign up to our newsletter on Groxio, there's also going to be a machine learning math session that's free. That's going to be the first week of June. I think the first Wednesday of June. Okay, so I want to talk a little bit about how machine learning works. So the idea is that we're going to build this generic function. I feel like I'm staring off into the middle distance by looking at people. So let me bring the faces over here. Now I can look at you. Okay. So machine learning is the art of building like a generic function that deals with layers of numeric data, and then having that function defined in such a way that it has these knobs and levers that you can turn, right? What do I mean by knobs and levers? Well, does anybody remember the formula for a line in junior high or high school algebra? What's the formula for a line?
X equal Y.
Yeah, so this is one. Okay, so what about a line with a slope and all that kind of stuff? What if I did a y equals, what's the general form?
mx plus b.
Mx plus b, right? And so if I write that in Elixir, it looks like that. And if I write it in machine learning style, I would say wx, where w is a weight that defines the slope of the line, and where x is potentially multiple dimensional or multi-dimensional data. It's easy for you to say, right? And this multiplication would be defined as a dot product multiplication, right? And this would be defined as broadcast addition, right? So basically there are rules for multiplying multi-dimensional data. So for example, if I want, what is a multi-dimensional list in X called? Does anybody know? Blank flow from Google. What's the Google machine learning library?
TensorFlow.
Yeah, so we're going to use a tensor, right? And so let's build a tensor, and let's build it out of 1, 2, 3, 4, right? And so that's kind of boring, right? That's a flat tensor, but we can reshape that, right? So I could say index.reshape, and I want to pass that a tuple with a new shape. And maybe I want this to be 2 by 2, right? And so now I have this 2 by 2 tensor, and I can call this A, right? And I can call this one B. And let's make this what's called the identity matrix, and you can guess why. So it turns out that if I do, if there are ones on the diagonal like this, if I do matrix multiplication, so if I say index dot, and then I could do A comma B. I should get A back. Yeah, and I do. Or there's basically element-wise multiplication that can, did I do that right? Multiply, okay. There we go. A comma B, right? And this is element-wise multiplication, and this just kind of multiplies the 1 1, 1 2, 2 1, and 2 2 together, right? So essentially, what I'm saying is that when you have this W X plus B, that gets really interesting when it's applied as a layer in like a long pipeline when that's applied as a model, right? And you can tweak, and it gets even more interesting when you can tweak those weights. And it gets even more interesting when you can add functions between them that are nonlinear, so that you can use this thing to make nonlinear predictions, right? So that's a neural network. And I know that this all sounds a little crazy, and it's difficult to understand. So what I'd like to do is, rather than throw this classic machine learning problem at you, what I'd like to do is implement a very well-known domain with just enough complexity so that we understand it, and it's nonlinear, but it's also it's non-trivial enough for our purposes, right? So I want to think about index and exon rather than thinking about the domain. So the game is FizzBuzz. So who can describe FizzBuzz to me? You guys know I'm very patient.
The interview problem, FizzBuzz.
That's it. Yep.
So for Fizz, you have to take a remainder with 3. So if it's 0, if you divide it by 3, you print Fizz. Or if divided by 5, then Buzz. Or if either 3 and 5, FizzBuzz.
Right. Did you catch that? So the idea is that it's a counting game, and each player is going to say a number. If that number is divisible by 3, you say Fizz. If it's divisible by 5, you say Buzz. And if it's divisible by both, you say FizzBuzz. And so if essentially we're going to predict something that looks like 1, 2, Fizz, 4, Buzz, and on and on and on, right? So eventually what we're going to do is write a helper. So what we're going to use index for is making a prediction or recognizing what the pattern looks like based on data. And we're going to carve a list of numbers into categories, right? So the categories are Fizz, Buzz, FizzBuzz, or else, right? And then we'll just have a simple helper function that passes an integer and a category. And if the category is else, we'll ignore the category and then we'll use the integer. Otherwise, we'll ignore the integer and we'll print the category, right? So this problem is interesting because you can imagine that it looks a lot like a lot of the problems that we see, right? So we're going to carve our integers into features. Is a number divisible by 3? Is a number divisible by 5? And is a number divisible by 15? So let's do that one first. So let's say we're going to build this function called mods. So, and I say mods for modular arithmetic. And so let's see. Let's just do an anonymous function, right? So, and gosh, I want to go like really, really low tech here, right? And so I want to say the remainder of n divided by 3, right? I'm not even going to do like anything beyond this, right? My feature for this number is going to be the remainder of n divided by 3. remainder of n divided by 5, remainder of n divided by 15, right? Okay, so the idea is that now I could take this mods dot 5, and what will this say? What will
Buzz.
this give me?
It'll say buzz.
Yeah, so effectively we're looking for a
sorry.
buzz.
Yeah.
Yeah, but that's right. So these features, the middle one is my buzz detector, right? So this is what we want Axon to learn, right? And the reason that we're doing this, never tell anybody outside of this room that we did not find this data in the real world by transcribing index cards, right? We worked hard and we scrubbed all of our data, but really we're just going to build it with a function, right? But I mean, what's happened is everybody has gone and done their research and listened to children play FizzBuzz around the world. And that's what we're collecting, right? And we're breaking it to features, right? So that maybe if this problem is a house problem, I'm looking for a zip code. I'm looking for the number of bathrooms. I'm looking for other chunks of data that I can carve into features that I can categorize, right? And thus assign numerical probabilities to them, or to assign a numerical probability like distance from employer, right? Like the size of the house in square feet, like the number of bathrooms. Presumably, when any of those things go up or down or in some predictable fashion, the price of the change, the prediction of the house can change, right? Okay, so the next thing that we need is we need a function for the thing that we're going to predict, right? So this is predicting the inputs. This thing is going to give me the outputs. So let's say FizzBuzz is equal, and I mean, why not do another anonymous function, right? He's never led us wrong so far, right? And let's do a cond. Okay, and so if the remainder of n is we need to do 15 first, right? Because this is divisible by both. Otherwise, this one is going to hit first or this one is going to hit first. So we need to do this one first, right? So if that is equal to what? To 0, then what should this say?
FizzBuzz.
Right. So FizzBuzz, right? Okay, so we're going to cheat a little bit. What we should probably be doing here instead is using Axon's features to translate those labels into numeric values, right? But so let's go ahead and just assign the numbers 0, 1, 2, 3 to FizzBuzz, right? And so what would that be if we're going? Let's see. What should FizzBuzz be? What should 0 be first?
Can it be nothing?
Okay,
Like
so
integers?
so 0 is going to be else. Cool. And so what is 1 going to be?
One gonna be fizz.
Fizz,
Gonna be
2,
buzz.
buzz. Okay, so we're going to say return a 3, right? Only let's think about this, right? What we want Axon to do is put this number in a matrix so that it can multiply it. It can throw this thing grind it through the sausage machine, right? We don't really want to know how it's made. And it's going to put out a number, right? And we want to bring the number closer to the goal based on our training input, right? So it's probably a bad idea to have a number 0 through 3. Probably what's better is to have a column, right? And 0 probability of 0, 0 probability of 1, 0 probability of 2, and 100% on 3. Got me? Okay, so let's do n comma 3. Okay, somebody help me? What's this going to be?
Zero, 1, 0, 0.
That's right. Right? Everybody get it? This is else, fizz, buzz, fizz, buzz. So this is going to be fizz, right? Okay. N comma 5. And then what's this going to be?
Zero, 0, 1, 0.
0, 1. Okay, so what we're doing is we're encoding this by hand, right? There's a function in the library that can do it. I don't know what it is. So I'm taking a shortcut. Okay, otherwise true.
One, 0, 0, 0.
Right. Okay, so now I ought to be able to say fizz, buzz. So what should I feed this?
I don't know, 30.
Okay, and this should say,
Fizz buzz.
Okay.
yep, which is
So
0001, right?
0, 1.
Okay. So now we need to build some data. We're going to split data in 2 ways, right? The first split is horizontal, right? So we're going to have training data and we're going to have training predictions, right? So there's a split between the data that we're going to use to basically feed this into our model and see what it comes up with, and then it's going to be off, right? Unless we're really, really lucky. Like we won't be this lucky, right? Like a billion, like winning 3 lotteries in a row lucky, right? So the prediction is going to be off, and we're going to use something called a loss function to define how far it's off. Okay? And so that's the first split. The second split is going to be between test data and training data, which will both, of course, be split between observations and values, right? And so the reason that we have a test train split is that once we train our neural network, there's a risk that we could overtrain, right? Not with this data set, but if we put too much data through the system, one of the things that can happen is you might have outliers, and it might learn the outliers a little bit too carefully, right? So if there's a house with the same characteristics, and Bill Gates, hey, bought the house next door, he didn't really care how much he spent, and there's only one Bill Gates that's shopping in this neighborhood, so nobody's going to get a price that. So overtraining would bring the house too close to the Bill Gates price, right? It would not handle the outliers correctly, right? So what we're going to do is we're going to verify. We're going to make sure that with a certain subset of the training data, or a certain subset of the entire data set, that it looks okay, even though we don't train with it. Now we're going to cheat a little bit. Our training data and our test data are going to come from the same pool, because there's only really 4 different types of numbers that we can deal with, right? Those divisible by 3, those divisible by 5, those divisible by 15, and those not divisible by any of them, right? And but we're going to pretend that our data is more complex, robust, rich. Okay, so let's take a look at, let's build some training data, right? And so let's just take a 4 comprehension. Let's say 4x is taken from 1 to 1,000. And then we're going to so we're going to take the mods. Let's be consistent, right? I'm going to blow up. So we're going to take the mods of n, right? And this needs to be So effectively, what's going to happen in the real world is that these tensors will be full batches, right? Ours is tiny. It's really small, but in the real world, you want a tensor for every batch, and it'll just peel one off, train, peel the next one off, train, peel the next one off, train, and then start over, right? Okay. So we've built this tensor. There's a chunk of values in it. There are, it is, essentially, this is the data type. We could probably do better with the data type. We could probably go like an unsigned 8 instead of a signed 64. We're not going to mess with that. We're just going to take the defaults all the way through, baby. Or I'm going to get myself in trouble, right? Okay, so now we need some test data, right? The test data is shaped a little bit differently. So let's do another 4 comprehension. So 4x n is taken from 1 to 15. And then let's go ahead and do, what do we want? We want the mods n, right? But for the test, for some reason, I don't know why, I haven't done the research yet. This whole thing should be in a tensor. Did anybody get tensor when I said that? It's a bad joke. I really apologize. You can leave if you want. Okay, so now we have the left side of the equation. I guess I'm mirrored, so it's the left side of the equation. So we want the other side of the equation now. So let's go ahead and build that for the training data. So let's call these the targets. Different communities call these different things, and sometimes in the Python machine learning community, you'll call them like I don't know. In the Julia community, they're Y's and Y hats, right? So the Y hats for the prediction, and then the Y's for the actual values. But so in the Elixir community, it seems like there's most of them are using these targets. So this one needs to mirror on the left-hand side of the equation. It's going to need to basically have the same form. But then what we're going to want to do with this, we're going to say nx.tensor. And so what do we need on the inside of this? The targets, this is what we want the thing to learn. So first there's a batch in here. I'm not going to make you guess that, but what do you think we want the system to learn based on the inputs that we give it?
Like if there's a pattern or something. Like
Yep. And what?
a way.
So basically, we've said we've calculated the inputs, right? So the inputs that we defined are right here, the train, right? So we said, hey, here's the modular division. So given this input, what do I want it to remember? What do I want it to be able to determine?
Like how, like the distances between the.
We just basically want to feed it the truth, right? There's no math here. We basically say, when you get this, predict this, right? So basically, this is the XY split. This is I've got this house for 2,000 square feet. There are 4.5 bathrooms. And it is in the lovely 37402 zip code. And it goes left-hand side of Zillow. And it goes for $792,000, right? That's the Y side, right? So the mods, these are the features. This is can you read it really, really small? This says, this is a square footage, right? This feature is the whatever, right? And then this is the sales price of the house. Though it's done in categorical form in our case, right? We want it to generate predictions that are reasonably close to these, right? So what we're going to be calling is FizzBuzz down here, right? So right? FizzBuzz of what?
Then.
Yeah, that's right. That's
And
right. So so now what we have is our split. We haven't computed the other side, the FizzBuzz of the other side, because basically what's going to happen with the test data is we're going to run it through the prediction and we're going to see what that looks like. And then we're going to use our eyes, right? Because we know what the FizzBuzz should say, right? Okay, so now we get to, now the easy part is over. You have to start thinking. This is where I start. I'm going to have to be checking my notes. So what we're going to do is build a model, right? And remember, this is the neural network that has a couple of layers. It has our input layer, right, that defines, hey, this is the shape of our data and everything. And then it has like the MX plus B layer, or WX plus B in machine learning speak, and that's called dense. It means densely connected. What it means is that we're using linear algebra to connect all of the weights from one model to all of the weights of another model, right? And then we need these things called activations, which are nonlinear functions. And they're just a couple of them that we always use in examples. One of them is sigmoid, one of them is tan H, and one of them is softmax, and we'll talk about that one in a second. We're going to use tan H, which is a slight improvement over sigmoid. Has some problems in very deep neural networks, doesn't have problems with pretty flat ones like the ones we're using. So we're going to have a couple of dense layers. The first, we're going to build inputs that have, how many features do we have? If these are our features, sorry, these are our features. I was trying to highlight on my on my screen. Okay, so these are our features. How many features do we have? Three, right. So so we're going to have, so let's say that we're going to have an input layer, right? And then we're going to say, then we're going to have a dense layer, then we're going to have a dense layer, and I think that's it, right? So let's fill out these details, right? So the shape of this input, we're going to have the number of batches, or sometimes this can be like the number, the batch size. We're going to let Axon figure it out so that we could pass in batches of different sizes, right? And in fact, you're going to see, you've already seen us define sizes in a couple of different places. What's the best way to do this? Yeah. So the test, how many observations are we passing here?
Was it 1,000?
In test right here. Can you see my screen?
Oh, for sure.
So how many? 15, right? And so how many in my train? 1,000, right? So we already know we're going to have two different batch sizes, but we don't have to create two different models, right? So what we want to do is specify nil here, and then we could let Axon figure it out based on the input size, right? And so how many features do we have for the inputs?
So just to clarify,
Yeah.
the features that you're talking about are like divisible by 3, divisible by 4, and default, right?
That's
Not by
right.
both. Oh, okay.
That's right. So we have 3 features. That's right. That's right. And you got them exactly right. Divisible by 3 divisible by
So
3.
divisible by both doesn't count as a feature, right?
It does. It's here.
Oh, it does.
Divisible by
Well,
15,
What
right?
about default though? Like,
Else we don't
Yeah.
have that as a feature, right?
oh,
We're going
okay.
to, so basically that's what we want our neural network to figure out. We
I
want it
see.
to take these features and we want it to learn the pattern in these features to divine
Okay,
the answer to this problem,
I see.
right? Okay, so now we have these features, right? And now we need to get this to a dense layer. So how do I chain functions together in Elixir? What's the operator that I
Yeah,
use?
pipe.
Yeah, the pipe. That's right. Right, and this I'm hoping is going to be axon.dense, right? And then this is going to be something in here. And this is, at this point, this is acting like a function, right? So it's a configurable function with parameters in it, but we don't care about that. What this is doing is actually setting up a model. It's actually building the metadata for a model, all the metadata that Axon will need later to actually do the training. Well, to do this part of the training, right? Well, this is the data structure that Axon's training model will train, right? There's metadata that will build up in the training step also, right? Okay, so let's talk about this. We said that we want an activation function. Does anybody remember? Tangent, tan H, yep. And then let's say that we want just 10 layers here, right? And why 10 layers? I don't know, because that's what a example that I built earlier used, and it seemed to work okay. The one that I built in Julia, and I haven't changed since. Okay, and so what about this one? So this is the last layer. How many categories do we want in our prediction? How many possible categories of numbers are? 4,
right?
That's right. And then I type 5, right? And then activation. We're going to call this one softmax. So what a softmax function does is it takes 4 discrete floating point numbers and converts them to probabilities that add up to 1. Right? It's basically related to the sigmoid function. You can look up the formula if you want to. I don't know it by heart, so I'm not going to tell you. Right? But essentially, you should look at this as we're going to have 4 numbers spilling out of this network. Higher number is a higher probability. And it is a formula for taking those and building representative probabilities. Right? Okay, so what I'm going to do is, if anybody could just pray a little bit. Okay, hey, that looks good. That looks good. Okay, so so how many inputs and outputs? How many batches are on our input layer? We don't know, right? It's flexible, so we left it as nil. And notice that Axon populated this all the way down, and it will fill this number out as the data gets applied in every batch, right? So how many input features?
3.
Right, and then we flow into the next one, right? Which is a dense layer. And so that means that there's going to be, that X is going to be a matrix. Well, what shape is that matrix going to be? Well, it turns out it's going to be 3 by 10. And I haven't learned Axon very well yet, so I don't know the order of that, which is rows and which is columns. It's one or the other. And so the 3 by 10, the reason that there are 40 parameters is that 30 of them are weights over here, right, on the W side, and the rest are biases that will all be added on. So think of the weights as things that determine the strength of the connection as the multiplication feeds down the neural network using the rules of linear algebra. And literally, it's just a function that's applying, like when you see multiplication, it'll be a dot product. When you see addition, it'll be like broadcast addition, and so on and so forth, right? So we fire in this input layer, builds our input, then fire it into the dense layer, Wx plus b. Everything gets piped through tanh, so that when this comes out of tanh, everything will be between -1 and 1, and proportionally so. And then we fire it into another dense layer. There are 44 parameters. This time it is 4 by 10 layer, right? Because there's 4 layers in the output and there's 10 here. That's 40 cells. And then, but this time it's the opposite, right? So the rather than the inputs, so 3 by 10, this is 10 by 4. And so the 4 determines the number of elements in the bias, right? So, and then we feed the whole thing through the softmax. And what does softmax do? Anybody remember? So softmax is the one that basically takes everything and distills it down into probabilities, right? So if you remember, we had this code way up here. These are probabilities that sum to 1, right? So if I fed that into softmax, I would expect something very close to this to come out of softmax, right? It might not be exact, right? Because it's a smooth curve and it might leave a little bit of a residual in the zeros, but it's going to be very close to that. And if I fed 0.25, 0.25, 0.25, 0.25 in, then I'm going to get the same thing back out, right? But it's just a layer that converts my vector to something that's a probabilistic predictive model, right? Okay, so now it gets a little bit fun because we've already done the hard work. Now we get to hand it off to Axon. So the first thing I'm going to do is God, did you see me sneak into Julia? I was in question mark to get help, and it's not that, right? Axon dot, and we want what? We want training dot train. Is that what we want? Let's see. Let me check my notes. I want training dot. Yes. So I need to define what a training step looks like, right? And so let's see what this says. Okay. So training step is going to take a model. Do we have one of those?
Yes.
Yeah, we do, right? So we built the model with all the layers. That's what we just did. A loss function, and luckily somebody else wrote that, probably Sean Moriarty. And then we get to choose an optimizer, right? So let's go ahead and take that. And what is it going to return? It's going to return a 2-tuple. Let's see, it returns a 2-tuple. I don't see it here, but it does return a 2-tuple. And the first thing is going to be the params. What are the parameters? What are the parameters of my model? These are my configurable knobs and levers, right? I don't know exactly what they are, but I know how many there are. There are 84, right? And when we change these weights and biases, the predictions will change, right? So it's going to give me the parameters back out, and then it's going to give me optimizer state, right? I don't want to carry that with me. I'm just going to underscore that to ignore it. And so let's say we want to start with a model. We're going to feed that into axon.training.step, and then the two pieces. Okay.
I think you're
So-
missing an equal sign.
What's that?
I think you're missing an equal sign.
I am, and I love you forever. It would have taken me forever to okay. So, and we want to, okay. So a typical loss function in machine learning would be something like the mean of the squares, right? So add up, so you take, so maybe you have your actual numbers are 2 and 3, and maybe your predictions are 0 and 0, right? So you square 2, that's 4, and then you square 3, that's 9. So the square root of 13, or I'm sorry, so no, where did I get that? So 4, so it's 4 plus 13 divided by 2, right? The mean of the squares, right? So that would be a typical loss function. That's not going to work for us though, right? Because we have this, our loss is a little bit more complex because we have this idea of categories, right? So what we're going to do is we're going to do something. We're going to use a categorical loss function, and we're going to use something called cross entropy. Okay, so that's my loss function, and now I need an optimizer, and I'm just going to grab the cheat sheet for this. The optimizer is axon.optimizers.add. Okay, and then I think that I'm passing a learning rate here, which basically I want to pass a relatively small learning rate so that it takes tiny steps. The trade-off is that if your steps are too small, it doesn't converge very quickly. And if your steps are too large, there are local maximas. So what we're looking for is like the lowest point in a curve, and we could overshoot and step all the way across. What the loss curve looks like. So particularly with flux, which works with gradient descent. Okay, so let's see if this is okay. Yeah, so that's okay. And we're going to pipe that much to, now we need to actually train it, right? So we need to do axon.training.train. And so the first argument we already have, which is a training step. So that defines what this looks like. And now we need to pass all the parameters that we've kind of worked to build, right? And so what 2 chunks of data would you expect that we would pass out of the train, the targets, and the test? What are the guesses? Do we need the test yet?
Nope.
No, right? Because that's to verify the model that we build. So we're going to need the data, which is train, and the labels, right? And remember, we're going to call those the targets, right? And then there's an option, epochs, and we'll say we're going to train for 10 of them, and let's see if we get anything out of this. Okay, yes. This is the scariest moment of the demo. Hopefully, we are going down in complexity here. I didn't mean hopefully we're going down as like the plane crash. I mean down as in the happy learning curve. Okay, so what's happening is we're effectively tweaking those knobs and levers using a technique called auto differentiation, also called autograd. So if you go back to calculus class, it's going to take that loss function, which is a bunch of e's and logs and squares and in a defined formula, and it's going to take that loss function and build a derivative, right? And then it's going to, so the derivative of a loss function defines how quickly it's getting worse in the dimension in proportion to every single one of those parameters that we've defined. Right. So what Axon is actually going to do is it's actually going to flip that on its head, right? Minus whatever it came up with. And it's going to take that tiny learning step and multiply it and update each one of the parameters by exactly that much. And that's it. And we do that, all the way through the whole batch size and all the way through the 10 epochs. And then, so the loss goes down, right? So if we look at this at the loss behavior, we started with a loss of a third or something like that. Is that bad? Well, I don't know. Yeah, it looks really bad to me. I mean, it's what the loss was when we started, right? And so every step, the loss goes down, right? Okay, so now we can start to make predictions, but the predictions are not going to be very user-friendly, right? So we could say axon.predict. So what are the things that we're going to need to make predictions? What are your guesses?
I mean, the model.
We got to have the model.
Some params.
Yep. And then we got to feed in data, right? And we need to feed the left-hand side. We have two sets. We have the training set, right? We also have the test set. Let's use the test set because it's smaller. And wow. So what the heck is that? I don't know. I don't know, right? So what we need to do is feed this through another step. So we're going to build a cleaner prediction. So we're going to say predict.
Just a question on the last topic.
Yeah.
So loss is just what I understand by the word, like you take a guess, and if you are wrong, that's a loss, and if you're right,
that's right. And you need an objective function for measuring that with a numeric value, right?
Okay.
And so loss is a function.
To define what?
Loss is a function that defines the distance between the truth and the model's prediction.
Okay.
Numerically. And a worse prediction has to give you a worse loss, or this won't work. Right. A good example is mean squared error, right? There's another example, absolute or mean absolute error, MAE. Like, for example, we could say my predictions are 1, 2, 3, and the actuals are 0, 0, 0. Maybe our losses just add them up. It's 6. Right? That can work, right? Normally, what you want to do is punish outliers much more severely, because an outlier usually is a symptom that something's wrong, and so that you haven't got the right curve yet. So what you do is you accelerate your predictions by saying like mean squared error, right? And this is effectively what's called I can't remember the name of the loss function. There's the loss function everyone uses with an activated. I don't remember. Sorry, I think it has to do with, I don't remember. I'm gonna misquote it, so I'm not going to. But basically, our loss function, you could actually look it up. It's a mathematical function, and I believe it is just cross entropy. It's in most of the papers. So there's two types of cross entropy. There's binary for like one category, and there's categorical for multiple elements in a category, right? Okay, so we're going to build this prediction function. So we're almost done. We have about 3 more lines of code, and most of it is just to make a user-friendly prediction once we get our categories right? So this prediction, we're going to take, this is going to be an anonymous function with n, right? And so what we want to do is we want to call axon.predict dot pre. And what does this take again? What's the first argument?
Model,
All
params,
params
and test.
in data, right?
And then the data, right? And so this data, let's build a tensor with just the data that we need, right? And so the data that we need, so we need that those brackets, that's a batch, right? So so we just need the modular division at n, right? And this is going to give me a whole bunch of these, right? Actually, it's just going to give me one. And we want to pick up number 0, right? And then I want to say which argument is the biggest, right? So now I can say predict, give me a number.
15.
15. What should this give us?
3.
This buzz, right? Like 0, 0, 0. Okay.
Yeah. 0 is, so 0, 1, 2, 3, right? So that's pretty cool. That's pretty cool, right? Okay, so now what we need to do is take that and let's take that and we need to convert, right? So what do we do with this? So we need to take so we're going to need not just the prediction 0, 1, 2, or 3. What else do we need to actually play the game? We need the integer. Yeah. Okay. So let's build a function, and I'm going to think ahead to we actually need like the label. And since I know I'm going to be doing an each with index, or I'm enum.with index, so I'm going to guess that the index is going to be second, right? And let's see. Oh, this is killing me. I think I know where I'm going to go, right? Actually, let's do this first. Let's say labels is equal to. Okay, so what are our labels going to be? So 1 is what?
Fifth.
We want to do atoms. Let's do atoms. 2, and that is buzz. And then 3 is going to be and then I'm going to say 4, or I'm going to say 0 is going to be nil. Do as I say, not as I do. Right. You'll see why in a second. So let's do this. Let's say convert is equal to, okay, so now we need a function, and we have a label, and we have an index. And so let's say that's going to give me this function in here, right? And so I'm going to say map.get labels index. Is that right? No, labels label. That could potentially get me nil, right? Everybody see what I'm doing? Because if this is else, I'm going to get 0, right? And that's going to feed me a nil. And so this is going to give me a nil. And then I could just return the number in that case. Right? So now I can say axon.predict. So that's this is going to be model, the params, and the test, right? And that's going to give me a bunch of functions, and I need, oh crap. I'm not an enum. I'm in a tensor, so I can't use my enumerable library. I bet I can broadcast. Let's try this. Let's try index.arg max. Ooh, look at that, argmax 2. Let's see if, so it went into both dimensions and gave me the biggest number in the whole thing. That's not what I want. That's uncool, Axon. What I really want is to feed this into one dimension. What is that? Axis 0, right? Okay. Damn it. You see what it went? It went to the wrong dimension. We have a 15 by 4, and it gave me. Oh, how about this? Oh, now that's cool, right? Said another way. 1, 2, fizz. 4, buzz. Fizz. 8. No, it's 7, 8. It's working. Okay, but this is still in a tensor, and I need to convert that. Oh, come on. Ah, look at that. Look at that. Oh, look at that. 2 flat list. Let's see what we got now. Oh, we have a list. We can we can use an enumerable. So enum dot map. What function do I pass this bad boy? No, I need a with index.
Yeah, with index and then pass it convert.
Let's pass a 1, right, for offset, right? Ah! And we have fizz buzz. So this is so amazingly cool in a language which wasn't supposed to be able to do this. It is amazingly cool, right? So I love the concept of, I love the concept of the way that you do machine learning, right? It seems so awful, right? It seems like you start with this generic function, and then you keep messing with its values until it generates the value that you want. Right? That's machine learning. And so there's a lot of math behind this. There's a couple of efforts going on right now. So if you follow Groxio, I'm going through a lot of the math in a language called Julia, in a framework called Flux, which is cool because Flux, though it doesn't have, so it's not my regular language because Flux doesn't have all of the knobs and levers for dealing with the data around the edges, right? It's where do I go? How do I sample the data? How do I massage the data? How do I build these pipelines with streams that are reliable such that I can extract the pieces? How do I get the, the machine learning onto like embedded hardware, all these kinds of things Elixir does very well. What it does is provide some concise math, right? It's a great language for expressing things and it has pretty excellent concurrency. So one of the things that I recommend is you can actually learn a lot of the foundational concepts in Julia and in Flux, and then transfer those very readily to Elixir. And so if you want to do that, you can subscribe to Groxio. Again, ping Maggie. She's at maggie@grox.io. And what we'll do is we'll give you the regular annual subscription price, which is, I don't know, like $13 a month, but you have to pay a year's worth. And we'll make sure that you get all the Elixir content and all the Julia content, and which everybody gets anyway, but you get to keep it forever. So, and that's it. That's all I've got. Let me take some questions. I know you've got them. Is that Sean Moriarty?
Yeah, it's me. I'm here.
Oh, great. I'm glad you're here. And I'm glad my demo worked.
It was a fantastic demo. I appreciated it.
Oh, man. So your work is so brilliant. I mean, it's just, you have minds exploding like, it's fantastic. It's nice to virtually finally meet you. And I'm a huge fan of your work, very obviously. So I love this. I love this framework.
Yeah, thank you. I appreciate it.
Yeah. Wonderful. Does anybody else have any questions?
I do have a question. Like, how much do you think this is like useful in product as opposed to like science or data analysis?
Okay, so I'm going to take that, and then I'm going to hope that we can lean on Sean to give an answer as well, right? So the problem with using scientific languages is that you get the strong numerical analysis elements of the language, but you don't always get the things that you get with Elixir, the reasons that we code Elixir, the excellent productivity, the abstractions, the pure functional nature, and then everything around the edges, right? Like, where do you get the data? How do you massage the data? How do you get these things into shape? And so what's been happening is that languages like Python, essentially the whole data science community has moved off of the traditional numerical languages and onto the Python language, even though it's not really ideal for their work, right? And what's happening now is that we're starting to apply those techniques and need the machine learning techniques. And we recognize that it's not enough to be able to call out to some other model somewhere else. It's very limiting to apply to call out to another model and then bring the data back to where you're working with it, right? So I think that what you're seeing is some of these techniques, like especially the auto differentiation, right? Especially the the modeling that you can do on the graphics processing unit. It's tremendously powerful to be able to do this in a language with your live views, with your gen stage, where you could sample data as it comes through, where you could present like living, breathing graphs in something that really has the potential to stand the test of time and production, right? So, I mean, I think that machine learning is really starting to accelerate. I don't think that this is the end game. I think that we're going to see, with some of the techniques that are used in X, we're going to see much more powerful applications in like curve fitting and things like that using just like some of the techniques in index, and especially the auto diff and things like that. So Sean, I'm sure I killed. Are you still here, Sean?
Yeah, I'm still here. No, that was a great answer. I don't really have anything to add. In terms of Elixir and machine learning, I think Elixir has a lot of cool features that make it conducive for machine learning, and that's why I kind of got involved. And yeah, I think the future's bright. It's very early on, but I think we're moving pretty quickly. So,
Oh, no kidding. No kidding. I mean, when I I left for like 3 weeks, and to do my to work on the live view book and stuff, and then I came back, and gosh, you're already like blasting through all the convolutional network layers, and you're all it just wasn't enough to get those in place. It's now you're building abstractions with streams, and the math is really so beautiful and cool. Really love it. Hey, it's really cool to meet you, and thanks for coming. And yeah, it's my honor, definitely.
thanks for.
Okay, Oliver, I'll let you shut us down.
Yeah. Hey, thank you so much, Bruce. Thank you, Sean, also for being able to attend. We do have a virtual happy hour that's going to be starting in just a moment in the Toucan room. If you weren't there for Codebeam SF, we generally call it, I think it's Codebeam Beat this year, then you may not be familiar with Toucan, but it's a really cool way to network. I think you'll enjoy it, and we'll be doing it from now on after these events. I'm posting the link one more time so that everyone can see it. There we go. So meet us in there and see if you can chat for a bit. Take care, everyone. Thank you.